I'm not sure about the live stream or.
Hi everyone, good morning. Congratulations on being here that early. It's early, I'm kind of slow. Maybe Martin is too, but we'll make it. All right, my name is Leo, this is Martin. We work with formal verification at the Ethereum Foundation. And we wanted to go through the idea of fully automated form verification and see how far we can go in terms of verifying actual real-world contracts as opposed to toy contracts, which we do play a lot when developing new features and fixing bugs, this kind of things. So I'm going to start talking about some experiments, and then Martin will take over to talk about some Hbm Internals, which is one of the tools we're going to talk about. And heads up, right after this talk, Martin will lead a formal verification workshop right across the hallway at room BF, or however it's pronounced. So we're going to be moving right away after this talk over there and run a few live demos and also chat more about everything. There's a lot of overlap between these two talks. Do you want to say anything first? Right. So the goal of this experiment was to run over a few examples and see what we can get from fully automated formal verification tools. So how many people here understand this overall? Okay, cool. So this is the first contract we're trying to verify. It's a Solidity token contract, a very simplified version of the usual ERC20 contracts we have. Of course, I removed a lot of stuff here because I wanted it to fit on the screen. So here we have the basic constructor that basically sets whatever amount to the owner of the contract, which is the sender. And here we want to verify functional correctness of the transfer function, which just transfers a certain amount from the message sender to someone else. And then we verify that the sum of the two balances does not change after this transfer. So we want to verify that this assert is true. It must always be true. Otherwise, we have a bug in our program. The second one is an AMM, so an automated market maker, which this is also a very simplified version of. In this contract, you can find this kind of contract in Uniswap and other exchanges, where you can swap one token to the other. So in these contracts, usually, so this is an example that I took from David Terry, also from the formal verification team. So here we have the contract that has two tokens that we will want to be able to swap, say, for example, DAI and USDT. And some actions you can do in this contract are you can join the contract giving a certain amount of each of the tokens. You can exit the market, or you can swap one token. Where is this? You can swap one token to the other. And the price for the swap is calculated over this constant formula that we have heard so much about, x equals x times y. And we want this constant to never decrease. So this is a property we want to prove statically. The next example is going to be the deposit contract. I'm not sure how much you can read from this. It's quite a lot of code, but this is not a simplified version. So this is the actual deposit function from the deposit contract that was deployed last year. So the deposit contract is the ETH2 deposit contract, where validators must deposit at least 32 ETH to be able to be a validator on the Beacon chain. So this deposit contract has a Merkle tree of other validators, and it was formally verified by runtime verification. We have Ricard here. I'm not sure if he worked on it, but he works for RV. And they first verified the Viper version, and then they the team that coded the contract decided to swap to Solidity because of gas costs. And this is the final version. And we want to prove that this assertion here, the end of this function, is never reached. So we want to prove that this loop always terminates inside this branch here. The next one is a snippet from the OpenZeppelin implementation of the ERC-777 token. What this token does is it's basically a normal ERC-20 token, plus it has the feature that it calls back both the receiver and the toker whenever a transfer is made. So there's this interface for the sender and for the recipient, and both of these functions in each contract, if there are contracts, they are called whenever there's a transfer. And the property we want to verify is that whenever these callbacks are called, so here tokens to send, tokens received, we don't want them to mess up with the total supply of the token. So these two properties are what we want to prove. Okay, so the experiment is basically to try to run some tools that are fully automated or almost fully automated, basically relying on a small and simple specification, where so far I only showed specification in terms of the assertion that we want to prove is always correct. But some of these tools will require a little bit of a spec. And if a tool is not here, it's because it either requires a more complex type of specification, like K, for example, or they are not fully publicly available, which I wanted to for this experiment because I just had a script that ran everything, so I wanted to just have a binary and run stuff. Okay, so the tools that I ran here were Mithril, which is a symbolic execution tool for hevm bytecode. It's very fast, but also very simple. It does simple things. hevm, which Martin will also talk about later. It does symbolic execution similarly for hevm bytecode, but also invariant testing, which Echidna, which I never know how to pronounce it. Echidna also does invariant testing. And then finally, the SMTChecker, Solidity verify and very smart, try to do unbounded model checking, so fully complete unbounded model checking, but on top of Solidity code. It doesn't handle hevm bytecode, only high-level Solidity code. And we want to run these tools and see which ones can prove or break the properties I wrote before automatically or with a little bit of spec. So if you can guess which tool could either prove correctness or find bugs in all the examples that I showed.
SMTChecker.
Any other guesses? Ah, now I spoiled. Sorry?
False positive?
Without false positives. Well, my question was related to without false positives. So here's the answer. None of them did it. One possible reason is not only automated, but formal verification in general is undecidable, which means that there's no possible algorithm or anything that will solve every single instance of a formal verification problem. So that's it. Okay, so it's undecidable. We can't really solve for general case. So there are several different approaches that have different pros and cons that a lot of people develop in the wild. And one very common approach is to either target hevm bytecode or target Solidity, high-level code. Some things against the approach of targeting Solidity is, first of all, you have to rely on compiler correctness. So everything you're proving at high level, not exactly on the bytecode you're deploying. So you still have to rely on the compiler being bug-free. And there's a lot to encode. High-level features, there's various data types, pointers, inheritance. There's just all sorts of really complicated stuff that's hard to encode when generating the formal model of the contract. Some pros of this approach are you have a lot more structure and information in the program. So you know what loops look like, you know what external calls look like, you know what state variables look like. So it's easier to simplify the problem sometimes. It's just the structure of the theorem you try to prove afterwards is just look simple in general. And this enables you to try harder problems that have loops, contract invariants, and all sorts of complicated stuff. And out of the tools that I mentioned before, the SMTChecker, Solidity verify, and very smart adopt this approach. The other tools, they target hevm bytecode. Of course, the first and foremost pro of this approach is that the results are basically what you deploy, right? You don't have to trust the compiler. You don't have to trust. Of course, you still have to trust the tool that verified it, but you just reduce a lot the level of trust that you need regarding a property. And it's generally easier to encode because you have stack, memory, storage, and you don't have all sorts of complicated stuff from the high-level language. Some of the problems here are basically the opposite of the other approach. There's not a lot of structure. So a state variable that just looks like x, and the other one it's a number, here it's going to be a slot in the entire storage. So it's much harder to track storage, external calls, functions, and all this kind of stuff. Another thing that gets a lot more complicated here is that the ABI encoding and decoding, ABI encoding and decoding code is all in the bytecode as well. Whereas in the Solidity code, you don't have that code. So when you start a function, you assume that the call data is going to be translated correctly into the types in the signature of the function. You don't have to deal with that at all, so it's a lot easier. So the experiment is use each tool in each example. First automatically, just tool example.sol, see what you get, and then try to power use the tool. So learn a bit more about the tool. And I think on average, I gave myself basically like an hour per tool, per example, to run it automatically, then learn the parameters, learn how the tool works, more or less, and try to get something stronger out of the tool. By the way, all the examples that I'm showing here are in this repo as well. Maybe not exactly a bit changed, but you can find it there. Also the presentation itself. Okay, so first trying to prove functional correctness of the transfer function. As I said, we want to prove that, so we have the person who wants to send funds and the person who wants to receive funds or a contract. They cannot be the same, and the method standard must have the amount they want to send. So we compute what the sum of their balances is before, we perform the transfer, we compute the balance of their sums, the sums of their balances after, and then we say must be the same. Is that correct?
Depends on your Solidity version. The two balance could overflow.
But if it, which one could overflow?
Balance 2.
But if it overflows, it just stops execution here. Oh yeah, sorry. Yeah, so this is Solidity 08. Yeah, so overflow doesn't exist. At this point, at least. Okay, so overflow and underflow reverts early. Said that, is that correct? Yeah, that's correct, right? So if we just run tool token.sol, these are the results we get. So all the tools can either prove that it's correct, or well, Echna doesn't issue proofs, but it didn't find any bugs, meaning didn't give any false positives, at least in the 50,000 instances it tries by default. So what if we make the transfer function buggy? Like, what is the bug here? Go ahead. Right, so this one is wrong, right? We're basically giving more to the sender himself, themselves, and this one's correct, but yeah, there's too many tokens here, and this should fail, right? So just running the tool on the example, this is what we get. So these 4 tools, okay, meaning they found the bug, and they give you a counterexample, meaning they tell you how to break the assertion and what the state is when you break it. Salty Verify did break the assertion, but it could not give a counterexample. And Verismart did not break the assertion. I suspect it is because Verismart doesn't really check assertions by default, even though it does claim to do so in the documentation. That's why I tried it. But I don't know, because in the log, it even says there were no assertions to be verified. So maybe this is a Solidity 08 thing. I don't know. Okay, sounds good. So the next one, swap functional correctness. We want to prove that this assertion is always true. Is it correct? Okay, we can go through a little bit. This might be a bit complicated. So the goal here is, so someone calls a swap function. They want to swap this token for this token, right? These 2 tokens must be these 2 here. Just the order doesn't matter. But they must be the same as these 2. And that's what these requires you to do. That's it. Then the way you compute the price for the swap is basically always trusting this formula here. You want this k equals x times y, where x is the balance of the market itself in token 0, and y is the balance of the market itself in token 1. So this cannot decrease, because if it decreases with time, it means that the market itself is losing money, right? So we first compute what the current ratio is, what the current multiplication is. Then we transfer to the market from the sender the source token they want to swap to the contract, give to the contract, which means that now the contract has more source than before, right? Then now we want to compute how many destination tokens we want to give to the user or to whoever called the swap function. So we take k, which is the previous multiplication, with both old balances, divide by the new source, right? The new amount of source tokens that the contract has, which is going to give us, this is just the same multiplication. So this is going to give us the new amount of destination tokens that the market has, which must be less than before, right? Because one increased, so the other one must decrease. Then we just subtract this. There's a minus here. It's a bit, right? We just subtracted from the previous amount of tokens the contract had in the destination token, and this difference should be the amount we give then to the user. Then we compute the same multiplication again. This must not have decreased, otherwise the market lost money. Is this assertion correct?
Yeah.
Any other guesses? I mean, the only other guess is no, so. Okay, so we're not gonna solve it yet, so that's why the interrogation mark. So first, when it's symbolic execution and model checking tools, they could not tell us anything. They did not prove the property, but they also did not disprove the property, meaning they just say, I don't know. So the next thing we can try is fuzzers. So here's hvm, and here's echidna, and actually both of them did break the assertion. And here's how. So hvm, actually, if I would have used a verbose mode, it would also have given the full list of functions. But here it just gives you a simplified look at the call data needed to break the assertion. And here echidna tells us that you can very easily break the assertion by first calling join, then calling swap. And this looks very simple. Okay, so the assertion is actually not true. But what did I have to do to actually get this? So this required a little bit more work than just the contract itself. So hvm works with DS test, which you can see here. And instead of verifying things in the contract itself, we want to write a test that uses the other contract and then tries to verify something on top of it. So here we have the same contract as before, but I changed the k, prev, and post to be state variables instead of local variables. And you can see that for the first iteration, both are 0, right? And for the second iteration, this one is going to have grown, so it should be true. Also, of course, it's more expensive because now they're state variables, but for the sake of proving the property, it should be equivalent. And here we have a function called invariant k, which is a view function that basically asserts the same property. So this is just the same as before. And here just getters for the two variables. So to use hevm fuzzing in this case, so we have a setup function that deploys the two tokens. We create an AMM with the two tokens. We create 3 users, which you will find in this repo, just didn't have space here. But what the users do, they're basically just interfaces to call the join, exit, and swap functions in the other contract. They just relay the calls. And then this contract was the owner of the 2 tokens. It just mint a bunch of tokens to the users and then just let them do whatever. And hevm fuzzing also requires, well, you can use this feature of the target contracts here. It's a function that returns a list of addresses, which are the addresses that are going to be used as the interface, as the front end for the fuzzing calls to be generated. That's it. And then we have this, so invariant fuzzing in hevm, it runs functions that start with the word invariant. And basically, this just calls the invariant from the contract itself. And then if this assert fails, this is going to fail, and then you get the result that I showed before. To run this with echidna, it was very, very similar. I used pretty much the same users, the same task AMM. I only didn't use the target contracts. And the echidna invariant fuzzing needs the function to start with echidna. And the difference is that it doesn't check for assertion failures in this case. You need to return a bool. So basically, instead of asserting, you just return whether the invariant is true or not, and that's it. And that was the result that I got before. Okay, so the contract was wrong. I think my next slide actually tells how to fix it. Does anyone have any idea how to fix it? I'm going to go back for a second. Do you know the answer? Okay, so the fix requires 2 characters.
Will you give us a hint?
I'll show you the hint. So the property that you actually want is, the property you actually want is that k post equals k. But for some reason, this cannot really be true all the time. That's why we say it's fine if it's greater. We just don't want to lose money. But ideally, in an ideal world, this should be equals and not greater or equal.
But you only have integer numbers.
Yeah, getting there?
What's the join function in Echidna output?
Sorry?
What's the join function in Echidna output? I think it's on the next slide. It said join then swap.
Right. So the join function, basically, you give, so you give both tokens to the market. Then you get like a share of the market. Then when you exit, you get tokens back based on your share of the whole pool. So let's go in the right direction. So the thing is, you have integer division here. So sometimes this division is not going to be an integer result, which means we have to round the output. And this is a solution with this plus 1. So this is how it is actually implemented, at least in this version of the contract. Because of rounding, basically. So basically what this does is, if the division is integer, then the property is equals, so no one gains or loses more money. But if the division is not integer, then the rounding goes to the contract, to the market. And that's why k can grow, but it can never decrease. So now both fuzzers say, okay, everything's fine. So that's as far as we got with this example. So the model tracker still could not prove anything, but the fuzzers can now give us good confidence that it is correct. Let me just see how much time I've spent. Did I spend 20 minutes already? Okay, I'm going to try to speed up a little bit. So trying to prove functional correctness of the deposit contract. We want to prove that this assertion is false. So running all the tools just like this, just with the contract as is, also no tool could prove anything. You get false positives, you get I don't know what's happening, all kind of results. But we can try different things. So when running hevm on this function, the main problem is that in the original contract, you can see that here there's 3 parameters that are dynamic bytes. And hevm doesn't support symbolic dynamic types in the input of functions it wants to reason about. But here you can see that these dynamic bytes, they actually must have a fixed length, all 3 of them. So pub key must have 48 bytes, with raw credentials 32, signature must have 96. They could be fixed types. The reason why they're not is historical when converting the contract from Viper to Solidity. And I'm not going to go into too much details. We can talk after, but yeah, there's a historical reason for that. But effectively, they could be fixed byte types. So that's what we change here for hevm. So instead of having a byte that must be 48 in the require, we can make the pub key 3 bytes 16 variables, which is 48. With raw credentials was already 32, and signature was 96, so we make 3 bytes 32 variables. And we can remove all the other requires because now the length is guaranteed by the ABI decoder. Just with this change, the rest is all the same here. Now we can, so hevm can now prove that the assertion cannot be violated. And it proves that after exploring 295 branches with assertion violations. And you may ask, well, what about the for loop? How does hevm know that the loop, does this include all the loop iterations? And it actually does, because if you take a look at the contract, you'll see that the loop is actually bounded by a constant number, and it can only run 32 iterations, not more than that. And hevm by default sets to 50 the number of times that an EVM CFG node can be rerun. So we know that here all the loop bounds, all the loop iterations are covered. But of course, this includes internal knowledge about the tool, right? I know that it's 50 because Martin works in the tool and he told me it's 50. So if you don't know that it's 50, then you could also use a parameter called max iterations for hevm, which I did try, but then it failed. It took too long. I don't remember why, but there were reasons. It proves like this, so we're good. When running the model checkers, they also couldn't do much. So Verisol couldn't do anything, and with Solidity Verify, which has a very similar approach to SMTChecker, it didn't support a lot of the Solidity features in this contract. It has a lot of weird stuff. Has encode packed, has hashing, has a bunch of things, and it just couldn't handle the language part of it, which means it couldn't prove anything. The SMTChecker, I got it to prove in the end, but it took quite a bit of work. So the first thing is, you see here, this line in the original contract, it basically tests that size is whether size is an odd number or not, right, by doing a bitwise operation with 1. And if it's 1, this means that it is an odd number. So the semantics of this line is just that. So I can replace that line by this line. So just doing mod 2 instead of bitwise 1. So the semantics, gas might change a little bit, but math is also cheap, so the behavior should be the same here. The reason why I changed this is the SMTChecker, or the solvers that it uses in the underlying logic layer, they have more problems with this type of operations than with this type of operations. So with this change, we make the problem much easier for the underlying solver. With the default solver that SMTChecker uses, which is called Spacer, it still couldn't prove it. So recently, this other solver, we use something called horn-based solving, and this other solver actually added some support we needed to running the theorems that the tool generates, called Eldorica. And using this solver via Solidity.js SMT callback, which is something that actually exists, plus setting a different abstraction option in the tool, allowed us to prove it quite quickly, actually, in less than 2 seconds. But you need to know that a second horn solver exists, and the tool actually can use that solver via Solidity.js, the JavaScript wrapper for the Solidity compiler, and you need to know that this tool has this abstraction option when turned off actually proves the deposit contract. So it took a little bit of work, but it worked. And here is part of the proof from the SMTChecker, from the tool actually. So this whole thing here is an inductive invariant for the loop before the assertion, which should prove that the loop always terminates inside that branch. But this is maybe 5% of the whole proof. So this last contract, I think I'm going to go very, very quickly through it because I took 25 minutes already, or even more. So this is an ERC777 token contract, which I mentioned before. When you make a transfer, it calls this function, tokens to send, in the sender, and it calls this function tokens received in the receiver. And what we want here, and this is from the OpenZeppelin official implementation from the repo, minus all the registry, authenticator, operator stuff, which is, I don't think is part of the actual standard. And there's a lot of stuff around it. And if you try to verify that, of course, it's going to take much longer. And I wanted this to be quicker, so I removed all that. And this still has the core of the ERC777 token. And I want those callbacks to not mess up with my total supply. So yeah, this must be true. And I'm going to go quickly over this contract because we're running out of time. And we're actually going to demo this contract live in the workshop. So we can talk more about this contract there if anyone is interested. But just very quickly, do you think this assertion is true with the contract as is? The rest of this contract is the same as ERC20. You can mint, you can burn, you can do whatever. So if I call this callback here in the sending contract, do you think this assertion is true?
Not necessarily. I mean, the receiver could do a reentrance and do a minting.
Yeah, you could do anything, right? Based on reentrance. So we think the property is actually not true, right? In this case, so Solidity Verify does say it's not true, but it doesn't give a counterexample. Verisol doesn't say anything. So this is just running the model checkers for now. And the SMTChecker does say the property is wrong. And this is actually one of the, in my opinion, one of the coolest features, is that it's going to, well, sometimes, not always, it's going to synthesize the reentrant call. So what it's basically doing is it's saying, transaction trace is you can deploy the contract UC777, this is the current state. Then someone calls burn, then which calls internal function underscore burn, which then calls the calls token to send callback thing that's going to call the sending contract. And this is that call. This is the untrusted external call. It's untrusted because we don't know who that contract is, right? It could be anything. It could have any code, and you have no idea what it's doing. So what the tool now does, it synthesizes calls that that contract could make back to your contract. So it synthesizes a reentrant call over here, calling burn, which then calls internal burn, which then is going to change the total supply of the contract, then breaking the assertion finally. And I also had to change some stuff in the contract. So counterexamples are actually, strings are pretty hard for counterexamples in the SMTChecker. So I removed like the string, the name of the contract, symbol of the contract, this kind of stuff. I just removed the state variables. And this already made it possible to get a counterexample. Because otherwise it would have to come up with values for those strings as well. And that's what it's hard here, and it doesn't really matter for the property. So we can test that. So this is a quick GS test. And here I'm just running a test, not really any symbolic check or any fuzzing. So basically we just have a your recipient contract. When it receives tokens, it then burns those tokens. Basically what the counterexample told us to do. When we run this is running with DevTools. You get a full transaction trace here. So I'm transferring, and here, this is the external call, tokens received. This is the callback in the receiving contract, which then calls burn, and then the assertion breaks afterwards. So we can forbid reentrancy by adding mutex to every public function. This is just one way, obviously, if you want to forbid reentrancy in this case. So we add a lock, and then every public function must use the modifier mutex, which means that basically we're forbidding reentrancy, right? So if you're trying to transfer, we're going to call the callbacks, but if they try to reenter and call mint or burn, which should also have this mutex modifier, then it's going to fail right at that point, right? It's going to fail the reentrancy guard, and the assertion should not fail if it's ever reached. So now running the test again, it still reverts, but now it's reverting because of the reentrancy check. So you see it reverts much earlier. So you try to do a transfer. This is the callback. It calls burn. It fails right away because of the mutex. So now if you rerun the SMTChecker on the same thing, so now we finally get a proof. And one of the new features coming up, this is, of course, a feature branch. It actually exports and tells you contract invariants and external call properties for reentrancy in the contract. And this still looks quite verbose and quite long. But basically, if we simplify this formula with just very basic operations, we get this property. So the solver inferred for us that this property is true for any external call that this contract might make. So if lock is true, this thing's maybe it's running out of battery. So if lock's true, it means that the total supply after the external call that you make to an untrusted code is not going to change, which is basically what we wanted to prove. Yeah, so I'm going to pass over to Martin to talk a little bit about Hbm Internals.
Okay, thanks. Just a little quick theory on how HVM does symbolic execution. HVM does a lot of different things, like we saw it in the previous examples, both doing invariant fuzzing and symbolic execution. And I won't really be talking about any of the fuzzing features or anything like that. I'll just go over a little bit of the symbolic execution stuff and the equivalence checking that it has, which also uses the symbolic execution engine. So it's basically just well, it starts as a normal EVM interpreter, and then it was generalized in March last year to also be able to deal with abstract arguments. So in the call data or in the call value or who the sender is and all these things. Not fully abstract in that you can't have abstract code, for example, It doesn't deal with abstract gas, but it has sufficiently many abstract arguments that it becomes interesting for the types of things that you normally want to prove. And as a trade-off, it's also quite fast at doing those things. So the way that it works is that it's executing the EVM, and some of the arguments that are in the stack or in memory are going to be symbolic terms, which means that we don't really evaluate the results immediately, but rather we build up this abstract syntax tree that we can then send to the SMTChecker to, or the SMT solver to consult whether this term actually is possible to fill with some real arguments. And as we're doing this, there may be branching points. And on the EVM level, these are all, the branching points are when you see the jump I instruction. And actually, we're doing an eager algorithm here where we don't actually consult the SMT solver for which path is reachable. We just explore both of them. And then at the end, we look at all of the final states that we get, and we look at the final states where our assertion might be violated, because often this is like a structural property that you can see without consulting SMT, to prune a lot of states early on. So if we know that we're looking for an assertion violation with the assert, and we have a bunch of cases where we have ordinary reverts, then we can just prune those from the state and we don't need to consult the solver at all. But for the ones that do look like they might be problematic, we take all of the constraints that we got from getting to this particular branching point, so all of the conditions under which we would have jumped to this particular branch, and we see whether it's possible to get to this branch. And to make sure that we're not getting stuck in an infinite loop somewhere in the code, we have this max iterations, which eternally keeps track of every time you encounter a particular jump I instruction. Okay. So that's how it works. It's an eager algorithm, and also this max iteration stuff. This can also explain what Leo was talking about when we were looking at the deposit contract, and we get different behavior when we change max iterations, because here max iteration sort of stops this eager algorithm in its tracks, because we need to make sure that we're not getting into this infinite loop. And so then once we reach max iterations, we want to make sure, okay, was this path actually reachable? And then we do a consultation with the SMT solver, and often this can be the bottleneck for the entire execution. So sometimes we run into a timeout here, and then the whole thing will not be as easy to verify. Okay, and since we are interested in performing this symbolic execution in a variety of different contexts, like we want to do it in DS tests where we have a very specific setup, we deploy all of the contracts that we're interested in, or maybe we're using mainnet states, or we're just like performing the symbolic execution on an arbitrary run of the contract. We want to assume that it's in any arbitrary state. We have a couple of different options when it comes to how we deal with storage when we're doing symbolic execution. And we have three options. So the first one is concrete. So this one actually fails if you try to do something symbolic with storage, if you try to read from a symbolic location, or if you try to write to a symbolic location. Because this one wants to be compatible with RPC. If you want to run symbolic execution against a mainnet contract, for example, then obviously you can't be asking for the mainnet value of an abstract location, because no client will be able to tell you what is at storage location X, where X is an unknown number. But if you say, I want the storage location, I want the value at 4, they can give you that. So when you're using concrete, you can use symbolic execution against mainnet states. And the other two are both symbolic versions. But but they make a different assumption on which particular state you're in that in the first one, which I call initial S, we're not assuming, we're assuming that everything that we haven't spoken about in storage is 0, the way it would be by default. We can still read and write from abstract locations, and we keep track of where we have read from and written to in this abstract storage mapping. But yeah, if we try to read from a location that we haven't written to before, we always get 0. So this is like, yeah, it's basically performing what you would get if there was no previous state besides what you have done in the setup function and your whole sort of dance that you do before you actually run the execution. Whereas the third one and the most general one, you're not assuming, you're not putting any additional constraints on the state of the contract. You're saying this contract can be in an arbitrary state, and whenever I read from any storage location, I can get any possible value back. And this is actually a bit of an over-approximation because you may have certain constraints enforced by the code of your contract, like you can't, for example, write to the storage location 13 ever. So if we were to have analyzed the contract completely, then we will know that this is 0, but if we're just looking at one particular invocation of a function, then we won't know that. So if we're reading from storage location 13 or X or whatever, we're just getting an abstract value back, and we're not putting any additional constraints on that. So when we're doing DS test, we're actually doing initial S because you're assumed to do all of the things that you want to do in your setup function. But when we're doing some other things like the equivalence thing that I'll be explaining to you what it is in the next slide, we're using this symbolic. So the fully unconstrained storage. Okay, so quickly about the equivalence checking that we can do with HCVM. So as I mentioned when I described the general algorithm of the symbolic execution that HCVM performs, it's going down all of these, it's going down the entire execution tree and looking at all of the leaves, right? So we can do that in 2 VMs at the same time. So we copy the entire VM state, and we change only the contract code. So now we can explore 2 VMs that differ only in the code of the current contract that we're executing. And we explore both paths of both contracts, or all of the paths in both contracts. And we look at all of the pairs of end states that we have. And then we compare every possible combination of these pairs and see if the constraint sets of each path are simultaneously satisfiable, and if so, if their results differ. Because this means that there is an input such that if you run it with a one piece of code, you'll get one result, and if you run it with the other piece of code, you get another result. That means that the contracts are actually different. And in fact, this is the only way something can be different, is you run it with the same input and you get different output. And so if there is no such pair, then these contracts must be equivalent. So that's how the equivalence checker works. And I think that's all I'm going to be saying about the theory of symbolic execution in HVM right now. And now I got to run to the other room and prep the workshop. But
all right, thanks. Bièvre, just like across the hallway, same floor here. Yeah, so we're obviously over time. I'm just going to skip to the very last one. I was not that optimistic. So just a few quick conclusions on actually the experimental part that I should maybe have put a slide before. So some of the automatic FV tools can be really powerful, even given which approach you're taking, verifying solidity, or EVM bytecode, or doing symbolic execution, or model checking, or this kind of stuff. But there is no tool that's going to do the job at every single time. So I would encourage everyone to actually use all of them. And each one of them is going to do something differently, and you might actually get a complete result if you use each one of them separately. Also, a conclusion of this experiment is that FV is still a very much an expert domain, and some very specific tool knowledge was required to verify, to extract the full potential of the tools and even verify these simplified versions of the contract. So you can only imagine what you need to do to verify the full version of the contract. So, for example, we needed to note that hevm does 50 iterations max, we needed to use a different horn solver, different abstraction options, so it was still quite in-depth knowledge required to verify these contracts, and of course playing with the tool, knowing the specifics of the tool, knowing the parameters and what things do differently is essential to get any good results out of the tools. So I don't think we have time for questions, but we're running over to the workshop. Thank you very much.